Hello everyone, this is Naga Lakshmi Devi, Assistant Professor, Department of Freshman Engineering, IARE, Hyderabad, Telangana. Now today topic is Taylor series expansion problems. First of all, the first problem is expand e power z as Taylor series about z equal to 1. Now the solution is let f of z equal to e power z be analytic within and on C. Therefore, it has a Taylor's expansion in powers of z minus 1. Here the given condition is z minus 1. Z equal to 1. That's why the powers expansion is z minus 1. Now consider the z minus 1 equal to W. That is nothing but z equal to W plus 1. Now convert into W e power z. E power z is nothing but here z is nothing but W plus 1. Substituting that here, then basis equal powers adding, otherwise basis splitting to the basis, that is e into e power w. E into e power w. What is the expansion of e power x? That is 1 plus x square by 1 factor 2 factorial, 1 plus x plus 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus up to so on. Like that here, just in x replaced by w, that equal to e into 1 plus x, 1 plus w square by 2 factorial plus w cube by 3 factorial plus up to so on. Now next, now the expansion of this one, the always z is greater than 2, z is greater than 1, w is greater than 1 here z is greater than 1. Then 1 plus, just substituting w is nothing but z minus 1. 1 plus z minus 1 plus z minus 1 whole square by 2 factorial plus z minus 1 whole cube by 3 factorial plus up to so on. Now it can be converted into simply we can write it as e power z plus e power z equal to e plus e into this part, e plus e into remaining this two, this complete formula, that is nothing but e z minus 1 plus z minus 1 whole square by 2 factorial. That means each and every one here it is n equal to 1, n equal to 2, n equal to 3, n equal to 4. In here also denominator is also 1 factorial. That is nothing but n equal to 1, n equal to 2, n equal to 3 up to so on. That's why we are writing as simply z minus 1 whole power n by n factorial. Here before e is there. That's why we have write here e. We have write here e. That equal to if z minus 1 is less than infinity. That is the power series condition. Now Taylor series expansion, simply we can write it as like this. Now next one. Now the second example is expand z into e power z as Taylor series about z equal to 1. Same before problem like that. Now here also same, z minus 1, here z equal to 1. That's why z minus 1 equal to w. That means w equal to, that means z equal to w plus 1. W plus 1. Now here again substituting z equal to w plus 1 each and every term here. Here two steps are there, z into e power z. In z just replaced by w plus 1 and e power w plus 1. Now z minus 1 equal to w, then here z equal to 1 plus w or w plus 1 into e power 1 plus w. That equal to e into, now splitting into two parts, e power 1 plus w. Now e into 1 plus w into e power w. E into 1 plus w is a constant term, we are common with that term. Only just expansion is only e power w term only. Why? Because Taylor series expansion like that. Now this expansion is already, we know earlier problem, we consider that one 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, like that. Here just x is equal to w here. That means 1 plus 1 factorial plus w square by 2 factorial. 1 factorial is nothing but 1. That's why I am not writing here. Plus w square by 2 factorial plus w cube by 3 factorial plus up to so on. Now again substituting the, what about z, we are considering that one. That is w equal to z minus 1. Now substituting here w equal to z minus 1. Now here already z minus 1 plus w is nothing but z. E z plus this complete structure. Now this is also we can write it as expansion method. Then that is e power z, ez plus ez square minus ez. minus Ez. That means both are cancelled. Otherwise, here also we are cancelled that one, no problem. Z. Only Z means E of Z, Z square plus Ez of Z minus 1 whole square by 2 factorial plus Ez of Z minus 1 whole cube plus 3 factorial plus up to so on. That can be written as simply summation. Already Ez square is there. Now, Ez square plus E into summation so Ez into summation n equal to 1 to infinity Z minus 1 whole power n by okay plus 1 by n factorial. Here Z is there, Z minus 1 is there. Now this is also not cancelled, that one better. Without cancellation is better. Simply you can write as this is 1 factorial 1 plus Z minus 1 by 1 factorial, that is better. That means E power Z, Ez, that is Ez into E power Ez. Now simply write it as Ez plus Ez n factorial, Z minus 1 power n by n factorial. This is the final solution. Now simply here we can write it as this one. Next solution. Next method is Maclaurin's series. As it is Taylor series expansion, a small changes in that place. It is x minus a. Here z minus a. Here just a equal to 0. Remaining as it is, we can use Taylor series expansion. What is the Taylor series expansion? Here f of z equal to z minus a to the power of n into f power n of a by n factorial. Here this is Taylor series expansion. This is Taylor series expansion. Now Maclaurin series expansion is f of z equal to z minus 0 power n, f power n of a, n is nothing but here 0 by n factorial. Here n is f dash of a, f double dash of a, f triple dash of a, like that. Now this is the Maclaurin series expansion. That is Maclaurin series expansion. Now the first problem is determine the first 4 terms of the power series for sin 2x using Maclaurin series. Sin 2x first 4 derivative parts. F of x is sin 2x, f dash of x equal to 2 cos 2x, f double dash of x equal to minus 4 is there, 2 into 2 4, cos derivative is sine, minus cos minus sine, minus sin 2x, again derivative minus 8 cos 2x, again derivative minus 16 sin 2x. Up to here we can finish. Now each and every term we are substituting a equal to 0, that means f of 0, x equal to a, that is 0, f of 0 equal to sin 0 value 0, f dash of 0 equal to 2 cos 2x, 2 cos 0 equal to 2, cos 0 value 1. Now sin 0 value 0, cos 0 value 1, that's why it is minus 8, sin 0 value 0, that is 16, 0, 16 into 0, 0. Next expansion, sin 2x expansion is sin 2x expansion. Sin x expansion is x minus x cube by 3 factorial plus x power 5 by 5 factorial minus up to so on. Now I am using that one sin 2x. Now x is just replaced by 2x. Okay, 0. The x derivative is first derivative, that is x equal to 0. Now that is 0 plus x into f dash of expanding here, substituting here z minus 0 power n, that is first condition 1, that is 2 into f power n of n factorial. N factorial is nothing but 1 factorial. Here n factorial is first is 3 factorial. Now that is nothing but here 3 means n equal to 3 means f triple dash, that is minus 8. Minus 8 is there. Before term is 0. Okay. Now the total expansion like that. Next expansion 0. Why? Because fourth derivative is 0. Next expansion is fifth derivative 32. Okay. Now each and every term, that is x plus first of all you are considering x plus x square by 2 factorial minus x cube by 3 factorial plus okay plus x power 4 by 4 factorial, like that. Here each and every even term is 0. Even term is 0. Even term is 0. Even term is 0. That's why I am substituting that only. We get only x term, x cube term, x power 5 term. That is, I am using that one. Simply we are solving like that. We are using two methods. Better, this is best method. That is our choice. Now, that is the Maclaurin series of the sin 2x. Similarly, z into e power z expansion in Maclaurin series. Okay, now f of z equal to z into e power z. We are applying uv. Applying uv means z into e power z. The derivative of uv equal to u into derivative of v plus v into derivative of u. Here, for example, we are considering z into e power z. U is z, for example. Z into derivative of vn means e power z. E power z plus v into e power z into z derivative is 1. That is z into e power z plus e power z is the derivative. That is the first derivative of the z into e power z. Now the first derivative is that one. E power z plus z into e power z. Now second derivative. E power z derivative as it is e power z. Z into e power z derivative is again z e power z plus z into e power z. Now this is 2 e power z. Now triple time. Third time derivative. E power z as it is e power z. E power z as it is e power z. Again z into e power z means z into e power z into e power z plus z into e power z. Using that one. Now next method. Next is f double dash triple dash fourth term. Derivative of fourth time. E power z as it is e power z e power z e power z e power z as it is e power z. Again z into e power z means e power z plus z into e power z. Now substituting each and every term. First of all, z equal to 0. Yeah, z equal to 0 means f of 0 equal to z equal to 0 means 0. Next, e power 0, one value. This one is 0. Why? Because this was 0. Next, 1 plus 1. This part is 0. 1 plus 1 plus 1. This part is 0. Next, 1 plus 1 plus 1 plus 1. This part is 0. That means f of 0 equal to 0. F dash of 0 equal to 1. F double dash of 0 equal to 2. F triple dash of 0 equal to 3. F fourth derivative is 4. Like that. Now expansion. Now what is the expansion? Z into e power z. Common with z, we get z into e power z. What is e power z expansion? 1 plus x square by 2 factorial plus x cube by 3 factorial plus up to so on. Now I am applying that one. 1 plus x means here z plus z square by 2 factorial plus z cube by 3 factorial plus up to so on. Next, what about the actually Maclaurin series? That is, and the expansion is there. That is f of z equal to z power n into f dash of 0 by n factorial, f power n of. Now the first series is n equal to 1 means z into f dash of 0 by 0 factorial. Next, plus z square into f double dash of 0 by 2 factorial plus z cube into f triple dash of 0 by 0 factorial. Okay, 3 factorial, like that. Now I am substituting that in this place. This is, now that is the expansion of here. Yeah, that is the expansion of that one. I am considering that one. That is Maclaurin's expansion. Now first step, z equal to 1. First of all, n equal to 0. Now substitution completed. 0, complete 0. Next, f n equal to 1. N equal to 1 means here 1. Z power 1 into f dash of 0 by 0 factorial. 0 factorial is 1. F dash of 0 equal to f of 0 equal to 0. The first condition is f of 0 equal to 0. I completed. Now the here z into f dash of 0, that is 1. F of z equal to, now substituting first term 1 plus, that is first term is 0. A z value, that is 0. Next, okay, part we saying f of 0 plus this one, that is Maclaurin's is expansion. Now f of 0 value is first is 0, that's why it is 0. Next, remaining z power n, that is z power n means that is z. First step we are splitting that one better. F dash of 0 plus 0 factorial. Oh no, n factorial, 1 factorial, that is 1 factorial that is 1 factorial plus z square by f double dash of 0 by 2 factorial plus z cube by f triple dash of 0 by 3 factorial plus up to so on plus f of a. Here f of a is there. F of a is nothing but f of 0. F of 0 value is 0. Substituting that one first. Plus z is as it is z. F dash of 0 value 1. Substituting 1. 1 by 1 factorial 1. Completed. Second one z square f double dash of 0. That is 2. Substituting 2 here by 2 factorial 2. Next z cube as it is z cube. F triple dash of 0 is z cube is 3. F double dash of f triple dash of 0 value is 3. Substituting 3 by 3 factorial. Similarly, next fourth one z power 4 f4 of 0 by 4 factorial. That means z power 4 is f4 of 4 divided by 2 is 4, then substituting 4 by 4 factorial plus up to so on. Now 0 is completely 0. Next z plus z square by 2 factorial cancel, 2 cancel, 3 factorial means 3 factorial is nothing but 6. 3 by 6 that is 2, 1 by 2 z cube plus 1 by 6 z power 4 plus up to so on. In Taylor series expansion I forgot that one, that is f of z equal to f of a plus z minus a whole power n into f power n of z a in by n factorial. That one. I forgot this one. I am applying that also here. Now this is the Maclaurin series expansion. These two problems also Maclaurin series important problems. Now the next method is Lorentz series expansion. If f of z is analytic on two concentric circles C1 and C2 with the center at Z0 and also in the annual region R bounded by C1 and C2, then at any point Z in R. Here f of z can be expressed as a convergent series of positive and negative powers of z minus z0 in the form. That form is f of z equal to summation n equal to 1 to infinity an of z minus z0 whole power n plus summation n equal to 1 to infinity bn of z minus z0 whole to the power of minus n. Now here we can write it as an equal to by using Cauchy's integral theorem, generalized Cauchy's integral theorem, we can write it as an equal to 1 by 2 pi I into integral over c1 f of z by z minus z0 to the power of n plus 1 dz, where n equal to 0, 1 to 3 up to so on. Now similarly again bn equal to 1 by 2 pi I integral over c2 f of z by z minus z0 to the power of n minus 1 minus n dz, n equal to 1 to up to so on n. 1 to up to so on. Now C being any simple closed curve lying within the annular and encircling the inner boundary of the annular region R. Here that means here a complete circle like this. Here another circle is there, another C1 and C2 is there, C1 and C2 is there. This is the our annular region R. This is region R. Now this is the annular region. This is the annular region. We are always finding this one, not in outside the region. We are considering here only. This is considering xi. The particular point we are considering xi. Otherwise z. That is our choice. This is the complete structure of this one. An plus bn. We find the annular part. Now proof of this one. Here C1, C2 is there. In outside the region we are considering C1 and inside the region we are considering C2. Outside the region is C1 and inside the region is C2. Now it is three ways of structure is there. Now here the complete structure, here we are finding the inside this part, complete part. That's why we are calculating this part to this area. A to B, C to D, like that. Now simply the proof of this one is let C1 and C2 be the circles modulus of z minus z0 equal to rho of 2, this part rho of 2, and Z minus Z naught is equal to P01, that is this part. Here P1 is always less than to P2, O1 is always less than to O2. Let f of z be analytic in the region R, R, and also C1 and C2, Let Z be any point on R. That's why I am telling here Z is a point of R. By introducing a cross cut ABCD, cross cut, just cross cut the only this area, including that one. I am using this area. That's why I am telling ABCD. Multi-connected region R is converted into a simply connected region. Multi-connected region is again connected with the multi-connected region. Then by Cauchy integral formula. What is the Cauchy integral formula? Integral f of z dz by z minus z naught is equal to 1 by 2 pi I into f of a. Now 2 pi I into f of a. Now f of z, 2 pi I into f of a, f of z, here z equal to a. Now same condition I am applying that one in C1 region. This is first part is C1 region and second part is C2 region. Now here applying the each and every one C2 and C1 two parts individually, then we get the complete ABCD region, that is C1 and C2 regions. Taking both the integrals in the anti-clockwise direction. Compulsory we are considering anti-clockwise direction. That's why I am applying like this, anti-clockwise direction. Since 1 by 2 pi I integral AB, integral over C, I am not writing that one because this area, that's why I am using AB. F of z by z minus z naught dz minus 1 by 2 pi I integral over CD, f of z by z minus z naught dz equal to 0. Now adding these two conditions, finally we get the 1 by 2 pi I integral over C1 f of z minus z naught dz plus 1 by 2 pi I integral over C2 f of z by z minus z naught dz. That is the equation number 1. Now applying this case in another Taylor series expansion, now we get the solution. As the proof of Taylor's theorem, we have 1 by 2 pi I integral over C2 f of z by z minus z naught minus z dz equal to Taylor series expansion. I am using that one. A naught plus A1 into z minus z naught plus A2 into z minus z naught whole square by 2 factorial. We are eliminating that one. Why? Because we are using in denominator part. That's why. Plus a n minus 1 into z minus z naught whole to the power of n minus 1 plus n up to so on. That is equation number 2, where an equal to 1 by 2 pi I integral over C2 f of z minus z naught whole to the power of n plus 1. Why? Because here n plus 1 terms are there. That's why n plus 1 dz, and remaining n of this is remainder. N is the last term. That is the Taylor series expansion last term. Always we are using remainder term also. That remainder term is this one. n of z equal to z minus z naught whole to the power of n by 2 pi I integral over C2 f of z by, here denominator can be split into two parts, z minus z naught whole power n, z minus z naught whole power n into z minus z dz, that equal to 1 by z minus z. I am explaining part by the one term, that is z minus z, that can be witnessed inside. I am using z naught. One cycle is there. That's why that is the z naught point. I am adding and subtracting that point. We get the two individual roots. Finally the roots can be splitting like this. I am common with the z minus z naught. Why? Because always I am using z minus z naught, and that condition. This is 1 minus x whole inverse method. 1 minus x whole inverse, that equal to 1 plus x square plus x cube plus up to so on. Similarly, 1 plus x whole inverse is equal to 1 minus, alternatively plus or minus. First starts with the positive onwards, negative plus like that, x square minus x cube plus x power 4 minus x power 5 plus up to so on. Like that. Here I need 1 minus, this is 1 minus, this is completely x. That's why I am using 1 minus x whole inverse method. Now the last term, this is the remainders method, that is x power n minus 1 plus x power n by 1 minus x. This is the last term, emended term. Substituting each and every term, that one 1 minus x can be replaced by a z psi minus z naught by z minus z naught. Continuing this process up to nth term and remainder term. This is nth term, this is remainder term. Then we get, in this condition, in above condition, multiplying by f of z by 2 pi I and integrating on over c1, we get integral 1 by 2 pi I integral over c1 f of z by z minus j xi, f of xi by z minus j dj equal to b1 by z minus z naught plus b2 by z minus z naught whole square plus up to so on bn minus 1 by z minus z naught whole by n minus 1. This is a remainder term, can be written as like this. Last term, then applying, completely we are in terms of summation term or integration term, simply we can write it as like this. Here completely this is converted into bn. This is completely converted into bn 1 by 2 pi I integral over c over c1 f of xi by xi minus z naught whole to the power of 1 minus n dz. Similarly, another term is there, that is 1 by f of z by z naught minus j. We are substituting that one. Now substituting equation 1, 2, 3, we get finally the condition is this one. This one. F of z equal to summation n equal to 0 to infinity an of z minus z naught whole power n plus summation of n equal to 1 to infinity bn of z minus z naught whole power minus n. Here why I am considering n equal to 0, n equal to 1. Now the condition is like that. A naught starts with 0 onwards. B1 starts with 1 onwards. That's why n equal to 0 to infinity. Here B1 is start with n equal to 1 to onwards. That's why n equal to 1 to infinity. Now this is the f of z is equation 1, 2, 3. The final solution is 4. Now Rn of z and Sn of z tends to 0. That is n tends to infinity. In denominator part is infinity means numerator is converted into 0. That's why I am applying that one. The remaining only up to here. Up to here. The remaining parts are this one. Hence, Lorentz theorem is verified. Now, that is the next two problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.